Good afternoon. Are you tired? Yes or no? No? I am tired. So you may expect a more confused lecture than before. But anyway, I leave these slides here so that you can go over them and find the correct version of this theory that I intended. This lecture on cryptography, this public lecture, disrupted our scientific journey. And we have to talk about not so beautiful things, right? Secrets, key distributions, and so on and so forth. Now we go back to the beauty of pure science, right? This morning we talked about classical information, and we found that there is one basic function, the Shannon entropy, that plays a very prominent role in classical information. It quantifies the amount of information that you can compress and the capacity or the rate with which you can communicate information without errors. I write it again for reference. So h of x, x means the source that is producing these outcomes, and the Shannon entropy is written in this. Sigma I, pi is the probability of outcome I, log of pi to the power of 2. And this is the average number of bits per day that you should use to compress information. And it also gives you the rate with which you can communicate messages from one place to another place without error. Now we want to generalize these things to the quantum domain. Right? This morning we talked about only classical things. We talked about bits, zeros and ones and messages and letters and so on. Now we want to talk about quantum states. And again, we do not talk about applications. Right? We talk about some basic questions, and we want to find the answers to those basic questions. And then we go. Why quantum computation? And Angela will talk about these things in his lecture. Today he also talked about teleportation and entanglement swapping and these things. And there are two main reasons for that. The first reason is that we now are able to load information into quantum objects, into photons, into atoms, into electrons, and so on, due to the advancement of technology. This is the first reason. And the second reason is that, for the first reason, these two guys were awarded the Nobel Prize in 2012. And the second reason is that, as Andrew talked about, there is an intriguing and very mysterious property of quantum phenomena, non-locality, entanglement, which enables you to do things that classically you cannot, like teleportation, like entanglement swapping. You cannot do these things in the classical. For these two reasons, we have to consider quantum information, right? And now we go to the questions. Okay, these are the guys. I told you that I'm giving a confused lecture because I'm tired. It's one of the sides. And these are the people who got the Nobel Prize for this. So these two properties allow us to do things that we were not able to do in the classical, like quantum computation that we talked about, quantum internet, quantum cryptography, quantum teleportation, and so on and so on, and many, many other things. Right? And some of these have been actually implemented in experiments. Okay? There is no need to write these things because I believe it's slides here. Right? Now, the purpose of this lecture is to answer three simple, basic questions. I write the questions and then I try to. The first question is this: how much information can be loaded into a quantum state? Suppose that you have a quantum bit, the state of an atom, of a two-level atom, of a qubit, of a spin. The question is how much information you can encode into this. This morning we learned about the quantity of information, right, by Shannon. Now we have a quantum object. We want to see how much information we can put in. This is the first question. The second question is that it's like similar to the question of this one. How much information can be compressed, quantum information? And the third one, again, is the parallel to the morning lecture. How much information can be transmitted without errors? Okay? The capacity of quantum change. We try to answer these questions one by one, and then the lecture will begin. Carl Shannon gave this entropy function, which I wrote here. This one is the Shannon entropy. And in the same way that this Shannon entropy plays a fundamental role in classical information, its analog, which is given by this formula, by von Neumann, plays the same role, almost the same, in quantum information. So, if we want to learn quantum information, we have to be quite familiar about this property of this function, the von Neumann entropy. And here it is the density matrix. So what is the density matrix? Because I do not know the background of all the students, some of you may have courses in advanced quantum mechanics, some of you may not. I try to talk about the meaning of the density matrix. Maybe most of you know it, but don't be bored, because one of the joys of life is to listen to what you already know, right? As a student, this is one of the good joys of life. So we want to see what is density matrix. As you heard in Angela's lecture, the wave function is the most complete description of the state of the system, right? It means that any observer, the average of any observer, can be calculated by this matrix, the operator n, which corresponds to this observer, and we sandwich it between these two states. But this is the case if you know these states. If you know that the state is psi. Most of the time, we do not know what is the state, right? For many reasons. And in that case, for example, suppose that you know that the state is psi1 by probability p1, and you know that the state is psi2 by probability p2. How do you calculate the average value of the observable n? Then you have two averages. One is statistical and one is quantum. It means that you have to sum these two values by the probability of p1 and p2 to obtain the final average. This means that the average value of the observable n is the sum of these two values. Then by some manipulation of quantum mechanics of Ket and Braz and so on and so forth, you can write it in this way. Write this psi 1 as a Ket, you bring it here, you bring this psi to here, and you end up with this formula. And if you look at this, it can be written as a more concise formula in this one, where rho is this matrix. So in the cases where we do not know which state we're dealing with, we can say that the most complete description is not given by the state psi, but it's given by a matrix, matrix rho, which contains both states and the probability of the states. Most of the time we do not know which state we are dealing with. That's the most complete description. So this is called the density matrix. Okay? Any question up to now? Okay. And once you have the density matrix, you can have all the information from the quantum system, and the von Neumann entropy stands for the analog, the quantum analog of this quantity, the quantum analog of Shannon entropy. Let's see how. So we have the density matrix. Then we want to calculate this. You remember the conversation of Shannon and von Neumann this morning about the naming of the entropy function. That was really the story. This conversation is not real. I have made it by myself, just for the fun. So the point is that how do we know to calculate this rho? To calculate the von Neumann entropy of this rho. We should not just put those pi's here, because these quantum states may not be orthogonal to each other. Right? You may have thousands of states here. You do not know whether the state is psi 1, psi 2, psi 7, psi 8, etc. So the right way to calculate the von Neumann entropy is that you should first form the matrix. The matrix is a 2x2 matrix because you are dealing with qubits. Right? Also, you are dealing with qubits. There may be many, many states here. There may be many, many states here. But after all, the matrix is a 2x2 matrix. You calculate the matrix. In the next stage, you diagonalize the matrix. When you diagonalize the matrix, the two eigenvalues come here. Right? Lambda 1 and lambda 2. The matrix becomes diagonal. And then you calculate this trace of rho log of rho with a minus sign. And then you end up exactly with this formula, but instead of pi, you have the eigenvalues, not the pi. The pi may go from 1 to 1 billion, because 1 billion states have been summed up to make those density matrices. But the final density matrix is a 2x2 matrix. So it is equal to minus sigma I, 1 to 2 for a qubit, lambda I, lambda I. This is the difference between von Neumann entropy and Shannon entropy. Any question on that? No? So you are enjoying what you are doing now. Okay? So this is the calculation of the von Neumann entropy for a 2x2 matrix for a cube. Again, so the first question: how much information can be loaded into a quantum state, into a qubit, into a quantum bit? Note that a quantum bit can have many, many variations, infinite number of variations, right? this quantum state, which is an arrow, can be in any direction, infinitely direction. How many bits of information we can load into this? You can load, for example, you can load A into this state, the letter A into this state, the letter B into this state, the letter C into this state, the letter D into this state, all the alphabets into this state. Is it true or not? So it appears that the qubit has a highly large capacity of storing information. Is it true or not? True. Right? Because a qubit has only two states. Classical bit has only two states. But the quantum bit has an infinite number of states. For these alpha and betas are complex numbers, and complex numbers are true. It's not true. It's not true. That's why I put this question first of all. Why? Because these states are not orthogonal to each other. They are not distinguishable from each other. You cannot distinguish these two states. You can only distinguish orthogonal states. If I send you a spin up state or a spin down state, you can distinguish. But if I send you a state like spin up, right? And a state like this one, you cannot distinguish. Sometimes you obtain spin up, here you also obtain spin up. So they are not orthogonal to each other. Okay? That's why a qubit, despite the possibility, the infinite possibility that all these alphas and betas have, the capacity of storing information is just 1 bit. What do we mean by that? This is the answer. And the answer, to explain the answer, the point is that information is not quantum. The word quantum information is a misnomer. It's not true. Information is always classical. We as humans generate information, receive information, and process information. Information is not quantum. State is not carrying information. It carries information, but the final information is classical. Right? And if you have a quantum state, in the laboratory you make measurement. And after this measurement, you have statistics of outcomes. Information is here. And you have to quantify the information from these statistics that you obtain in the laboratory. Right? Nothing more. For example, suppose that you have a spin up in the z direction, right? Then you make a measurement in the x direction. What you obtain is that you obtain 50% of the, almost 50% of the spins go up, 50% come down. If you do a measurement in the x direction, you agree? So here you have a probability of 1/2. And the Shannon entropy, the Shannon information from this formula, because the outcome is always classical, the Shannon entropy here is 1 bit of information. If I tell you that this ball went up, I have given you 1 bit of information, because you couldn't predict that this single ball, this single spin will go up or down in the Sternberg experiment. You agree? This state, its information content depends on what kind of measurement you are doing. Right? So here you do not know a particular spin will go up or down. If I give you an information that this spin went up, I'm giving you information. 1 bit of information. You cannot predict. So the information content depends on the kind of measurement that you have. On the contrary, this is related to the previous slide. Again, I have a spin up in the z direction. I'm doing the measurement of S of x, and the statistics that is produced by this measurement is this one. Every time we obtain one bit of information. Do you agree? If you do not agree, I will come down. On the contrary, if on the same quantum states, spin z in the up direction, you do this kind of measurement, right? All the spins go up. You agree? Because you are doing a compatible measurement. And the statistics that is produced is like this. So if I tell you that the first ball went up, second ball went up, I'm giving you no information, because you already know. Right? It's predictable. So the information content depends on the type of measurement that you're doing. And in any case, like this one, which I have an arbitrary state, like this, and I'm doing a measurement, every time that I give you some information about the fate of one of these balls, one of these spins, the information that I'm giving you is just a channel information for one bit, and never this amount of information exceeds 1 bit. I'm always giving 1 bit of information at most, depending on the type of measurement that I'm doing. So the answer to the first question is simple. In 1 qubit, we can at most store 1 bit of information. And that depends on the type of measurement that we are doing. If we do a clever measurement, we extract this 1 bit of information. If we do an unclever measurement, it's lost. This is the first part. We go to the second question. Okay. Coffee break. These are weird for coffee breaks. How much quantum information can be compressed? The same question that we asked about Schematic. Right? How much? And you can guess how much, because all the formulas are similar, quite different interpretations, but the formulas are similar. Oh. This is rather a little bit more technical. Suppose that we have a quantum source, like a quantum computer. This quantum computer has made some sort of calculations, and now the data is transferred from this quantum computer to another quantum computer. From IBM to Google, from Google to this institute, from this institute to a client, and so on. So information is produced by a quantum source. We mean a sequence of quantum states are being produced, right? They are the result of some calculations, some quantum process, some quantum information process, some information entity. So we have a quantum source. A classical source produces bits of zeros and ones, right? A quantum source produces qubits, states in different directions, infinitely many directions. So this is our quantum computer, which is producing these states, right? And these states are, let's call them phi 1, phi 2, phi 3, phi 4. Like the morning lecture, A, B, C, D. We have 4 alpha letters. No, we have 4 states, phi 1, phi 2, phi 3. Okay? And these states, suppose that they are orthogonal. Okay? Suppose that they are orthogonal. And we want to store the result of this calculation of this quantum computer in some sort of qubits, some, for example, optical lattice, some sort of ion trap. And then I want to come tomorrow and take this ion trap and then do the calculation again. The question is, how many ions I need? How many qubits I need? The question that you asked this morning. Suppose that we have some sort of quantum hardware. I have received some quantum states, huge number of quantum states. I want to check how much qubits I need for this quantum state to store the information, to store these quantum states in these quantum hardware, because quantum hardware are very expensive. I cannot be generous and use many qubits that are available. So I have to be very careful. I have to compress all these quantum states into as low as the number of qubits that I can, like ion trap or optical layers. And then tomorrow I want to come back and deal with these states. How many qubits I need? That's the question of compression. And if these states are orthogonal, the answer is easy. If they are orthogonal and completely distinguishable from each other, I use them like this. Oh, sorry. Again, some of these slides that disappear. I'm sorry. Okay. Okay. I have to write. So if these states are orthogonal to each other, suppose that I have 4 states which are orthogonal to each other, suppose, then this is phi 1, this is phi 2, this is phi 3. For example, they can be the 4 Bell states. When I want to store them in the qubit, I store this phi 1 into the states of 2. It's 0 and 0. Phi 2, I store them into 0 and 1. Phi 3, I store them into 1 and 0, and so on and so on. So I need 2 qubits to store the content of these 4 states. Tomorrow that I will come, I will take these 4 states from my hardware and do some operation on them to turn them back to the Bell states that were given to me and continue my calculations. But storage, for storage, I need only 2 qubits, if they are orthogonal to each other, if they are distinguishable. But suppose that they are not distinguishable from each other. And, oh, sorry, and they, I told you that I'm giving you confusing. Forgive me. Suppose that they are with these probabilities, right? With these probabilities. They are orthogonal to each other, but they are given with these probabilities, right? With these probabilities. Then again, I use the coding that I use in classical. I encode this into 0, encode this into 1, 0, 1, 1, 0, 1, 1. This was the case if all the probabilities were equal. If the probabilities are not equal, or this sort, 1/4, 1 second, and so on, I use this type of encoding. And this encoding means that the number of qubits that you use, the average number of qubits, do you remember how much was it?
175.
1.75. You need 1.75. Because this is the amount of Shannon entropy. Since all these states are orthogonal to each other, you can use the Shannon entropy for storing them, because there is no much difference between these 4 quantum states and 4 classical signals. Right? You have just to store the label of these states. State number 1, state number 2, number 3, or number 4. They are distinguishable. And number 1, 2, 3, and 4 means the letters A, B, C, D that we were using this morning. So you use classical coding for it. But suppose that the states are not orthogonal to each other, right? As the colors show, there are some overlaps between these states. They are not orthogonal to each other. So you may confuse one state for the other. They are not orthogonal. then what do you do? Or what is the answer? Can anybody guess? What is the answer? These states are not orthogonal. The guess should be easy from all these introductions.
Taking average?
Sorry?
Calculating the average of spin?
No. You should guess from the what I have written there. I have raised it. The first letter of this answer is V. I give you a hint. Or F. Von Neumann entropy. Von Neumann entropy. We should use the von Neumann entropy. It means that you calculate the density matrix rho with these probabilities, right? And these states, and you calculate this rho. You obtain a 2 by 2 matrix, and you calculate the von Neumann entropy for that. The von Neumann entropy for that will give you the amount of space, the amount of qubits that you need. And since these states are now similar to each other, they are not completely distinguishable, right? They have some overlap. You need less number of qubits. Perhaps you need, for example, 1.2 qubits, depending on the probabilities and depending on the states, whether they are orthogonal to each other or not, or what is the angle, right? So it depends on the states and the probabilities, not just the probabilities. This is the answer. You calculate rho, and then you calculate the von Neumann entropy. This is the, and if you remember, this morning we talked about typical sequences. Remember that all the sequences should not be taken care of. The number of total sequences is huge, 2 to the power n, right? And we understood that the number of typical sequences is lower. That's why compression is possible. The concept of typicality comes also here. In the quantum domain, you also have the concept of typicality. But instead of typical sequences, we have typical subspaces. You know that states live in a Hilbert space, right? If you have, for example, n qubits, n consecutive qubits, you have a huge Hilbert space. The dimension of the Hilbert space is 2 to the power n, right? And if you want to store any state in this huge Hilbert space, you need n qubits, because the dimension of the Hilbert space is 2 to the power n. So you need, for that hardware, you need n ions to store these large states into that hardware. But the point is that not all the states are produced by this quantum source. This quantum source produces typical states in a typical subspace. Graphically, this means this. This is the whole Hilbert space, right? Its dimension is 2 to the power n, if you have n qubits, right? Each of these qubits is 2-dimensional, because you have qubits. If you have n qubits, right, the dimension of these Hilbert space in which these sequence of qubits live is 2 to the power n. You agree? Right? Understand? 2 to the power n is the dimension of the huge Hilbert space in which these string of qubits live. But depending on these states and phase and so on, you can prove that the sequences of these states do not occupy the whole Hilbert space. They occupy subspace, almost. A subspace which has a lower dimension. All of them lie near subspace. And this subspace has a lower dimension, 2 to the power n SL. Exactly similar to the Shannon entropy. In the Shannon entropy case, we talked about typical sequences. Here we talk about typical subspace, a smaller subspace, right? Which has this dimension. And since all these states lie in this dimension, lie in this subspace, with this dimension n times s of rho, then I need a lower number of qubits to store these states. Suppose that s of rho, for example, is 0.5. It means that for each state in the top, I need only 0.5 qubit per state. I can still pause for a moment for questions and so on. And note that this is true as you use larger and larger strings of qubits. This is the philosophy of compression, quantum compression. That's why we can compress quantum information or quantum states. Right? Questions? Again, coffee break. So we come to the final question. How much quantum information can be transmitted without errors? Again, this is the analog of question that we asked this morning. How much quantum information can be transmitted without errors? Tomorrow we will talk about quantum errors. They are really very bad things. These are really disastrous things. But we will deal with that. But for now, we know that there are quantum errors, and we want to communicate without errors. So the question is, what is the capacity of quantum channels? In this part, we cannot give an analytic answer, we just can give you the answer. Or I can tell you what is the difficulty. In fact, I will not even give the answer, because the answer is complicated and it doesn't help us too much to learn the answer, the expression of the answer. In fact, the expression of the answer is not easy even to write, but I will give you an idea of why the concept of capacity is much more difficult in the quantum domain. Right? That's it. Okay? The basic point is that in the classical domain, you have only one type of capacity. You have classical bits, strings of bits. You send them through the channel. The bits turn into 0 or 1, they flip, and then you make the compensation for the error, and then you find the answer at the output. And you have to calculate only one type of that, one type of capacity. There's only one type of data, bits 0 or 1, and there's only one type of error, so everything is under control. You have one type of capacity. In the quantum domain, you have many types of capacities. And each of them has its own difficulty in definition, in calculation, and so on and so forth. So it's a headache to even think about quantum capacity. There are many different kinds. The first one is that you use a quantum state to send classical information. You want to send bits, strings of zeros and ones, classical messages, classical bits, but you want to store them into quantum states and send them to destination. At the destination, the receiver picks up these classical states. You may ask why we do this. Why you do not use a classical channel for sending classical strings? Why? What is the answer? We like to. This is the answer. Or we want to, because the channel is quantum mechanical. We do not want to load a bit of 0 or 1 into a large packet of electromagnetic wave. We want to increase the rate of information transfer, and we want to encode 0 or 1 into the polarization of one single photon. And then the rate will increase, of course. In the future, instead of the present carrier, the carriers will be microscopic, so they have quantum mechanical behavior, they obey quantum mechanics, and the carriers will be quantum. But you use these quantum channels for transferring classical information. You want to use a quantum states, the photons in a quantum, for example, channel, to transmit the information of a football match. The football match is not quantum, it's classical. The music is classical, but we want to use a quantum channel because of its efficiency to transmit it from one place to another. So, the first thing is that the first type of capacity is classical capacity of a quantum channel. It has its own formula, which is not even so easy to calculate. The second one, quantum capacity of quantum channels. So you use again quantum channels for transmitting quantum states. For example, here you have a quantum computer. It has produced some quantum states in the middle of calculation. And you have to transmit this quantum states from one place to another place, from Google to IBM. You have to transmit the quantum states. You do not do it to make measurement and collapse everything to classical things. You want to transmit the quantum states from one place to another, right? You do not want to make measurement because we are in the middle of calculations. Or you have quantum internet, or you have many sorts of things. So quantum states are being transmitted from one station to another station. This is called quantum capacity of quantum channel. This has its own definition, its own formula, its own complications. The third one is entanglement assisted capacity of quantum channels, like teleportation. You noted this evening with Angela's talk that we can do teleportation. In teleportation, you have a channel between Alice and Bob, a classical channel, plus a source of entanglement states. Or you want to do something like entanglement swapping. So this is communication assisted by entanglement, right? You have an entanglement between Alice and Bob. This is different from quantum channels that I described in the previous slides. This is called entanglement assisted capacity of quantum channels. The teleportation is one example. This has its own complication and definition and so on. And there are other also types of definitions of capacity. In all these capacities, the fundamental entropy, which I wrote, trace of rho, log of rho with a minus sign, plays an important role. But of course the formula is not simple because there are many things. But it is the core concept, the fundamental entropy. The calculations of these expressions are extremely difficult. But if you are interested in go to this domain, then you will consult scientific papers. Another role of fundamental entropy.
Vahid, can I ask a question?
Yes.
So given what you said before, that eventually information is for us, so it's classical at some point, why wouldn't you take the classical capacity, whatever the name was, as the best one?
What is your alternative?
No. Why wouldn't you take the first of the
I see. Because
as the most important one, the classical capacity?
No, I didn't say that it's the most important.
No, my question is why wouldn't you say so if information is classical at the end of the day?
Information is classical for Alice and Bob.
Yes.
Between the transmission, the errors are quantum.
Yes.
Because you encode these classical bits into quantum states.
Yes.
The quantum states at the beginning are orthogonal to each other, but then they overlap.
Yes.
So you have to deal with this.
No, my question was about the different capacity definitions that you give.
Okay.
Why wouldn't you single out the first one as the most important one?
You are right, but if you think about the second one, for example, in the second one, if you have quantum computers, then you want to send quantum states from one place to the other.
Okay.
Then maybe yes, we can say that the first one is the most important, but the second one is also there.
Okay.
Teleportation is also there as the third one, and so on. And how much time I have? It's over?
Take a few minutes more as you
A
left.
few minutes.
As you left.
The final role of quantum von Neumann entropy is the measure of entanglement. We are all talking about entanglement. It has many, many good features. It has many important properties. It allows us to do quantum internet, to do quantum teleportation, and so on and so forth, non-locality, everything. But you can ask how much entanglement, right? You know that we can do teleportation by this kind of states. These are the bed states. You can do perfect teleportation with this one, right? Now I give you this one. This is it. How much you pay for this state? You do not have that state in your laboratory. Okay? And I come and I propose to you as Bob and to you as Alice, and propose that I have this kind of states. How much you buy? Suppose that this state worth $1 per entangled states. How much you pay for this?
Cheaper than that.
Exactly. It's cheaper than that because this is the most important source. You can do teleportation with this, but you cannot do teleportation with this. But how much cheaper? How about this one?
According to program,
How about this one? How much you pay for this one? It's even, why it's even cheaper? Because it's closer to the product state. It's closer to a product state? This one? Okay.
Yes.
You agree?
it's more stable than that.
Stable is not, because it depends on the, this state is closer to this, right? Because of these probabilities. This state is far from it. But like any other thing, like any other valuable thing, if you want to value something, if you want to value your lira or dollars or euro, what do? You go to an exchange office, right? You take your money to an exchange office and give these states, you say that I have 3 of these states. How much you buy? Take these 3 states from me and give me 1 of these states back to me. And the exchange office here means a technical sense. It's quite important. Because these Alice and Bob are far from each other. One is Istanbul, one is in Ankara. These exchange offices, one is in Ankara, one is in Istanbul. They cannot meet each other. Alice and Bob cannot come to a common place and do the experiment. They are far from each other. One qubit is with Alice, one qubit is in Bob, and they can only do classical communication. They can call each other, and they can do local operations in their own laboratories. They cannot meet each other. So the problem is that they should do local operation and classical communication. It's allowed. They can call each other to tune their experiment with each other, their measurement with each other, their local operations, unitary operations, and so on. But all these operations should be local. So when they do this, if they can produce from 4 states that I have given you, 1 bed state, sorry, then the value of entanglement of one of these states is just 1/4. It's quite reasonable. Do you agree? I give you 4 states, you give me 1 full Bell state. So the value of this is 1/4. Right? And then, if you again write on the paper, sit and write on the paper, you will find that the value that we have found for the exchange, right, in the limit of large number of Bell states, again you use the concept of typicality, typical subspace, do some mathematical calculations, and you will find that the amount of entanglement of this state is nothing but the fundamental entropy of the reduced density matrix. This is the formula, and this is the role that fundamental entropy plays in measuring entanglement. Entanglement has become a valuable resource in quantum technology. Like any other resource, you have to quantify it. How much entanglement values, how much entanglement this state has, how much entanglement that state has. And the exact formula and the correct formula is given by the fundamental entropy. For the pure states, you take the states psi, AB, you calculate the reduced density matrix of one side, it doesn't look the rich side, and then you calculate the fundamental entropy. That's the value of the entanglement. So this is the schematic way that you have to do. This is the Alice part, the exchange office of Alice part. She can do any sorts of measurement and operation on all these qubits together. That's why I have drawn this box, huge box. This is the Alice part. Then they can communicate with each other. They start from this amount of semi-entangled states, and they come up with these states. The rest is garbage. It's not valuable for any kind of quantum information processing. But these are pure Bell states, complete Bell states. Then the exchange office, which is in technical terms called local operation and classical commutation, gives you the amount of entanglement in the form of von Neumann entropy. Thank you for your attention. Thank you.